Hey everyone, and welcome. We're about to jump into one of the biggest questions in AI right now. With models like GPT-4 being so incredibly powerful, what could possibly come next? We're going to look past the hype and get into the nitty-gritty of AI architecture to see how the next generation of AI is actually being built. Let's dive right in. To really get what's happening, you have to start with this quote. It's such a powerful idea. The transformer, the engine behind this entire AI revolution, well, it isn't the final destination. Not even close. Instead, we're going to look back on it as the beginning, the moment we really understood the power of building with smart, reusable pieces. It's like it taught us a whole new way to create. And yeah, that leads us right to the million-dollar question. If the transformer was just step one, what's step two? What does the future of AI even look like? To figure that out, we've got to go back to first principles. To see what's beyond the transformer era, we can't just ask, hey, what's the next hot new model? No, we need to ask way deeper, more fundamental questions about how these systems are put together from the ground up. And it really all boils down to these three things. First, what are our new Lego bricks, our fundamental building blocks? Second, what are the new instruction manuals for snapping them all together? And third, how in the world do we teach these super complex new things to learn well? These three questions, they're going to be our roadmap for this whole explainer. So let's start with those building blocks. Think about it like this. For the last few years, we've basically been building with one amazing but kind of limited model kit. Now it feels like we're about to be handed an infinite box of all sorts of different Lego bricks, and each one has its own unique superpower. Okay, so the very first problem we need a new brick for is the Transformer's biggest weakness. Its secret sauce, a mechanism called attention, is brilliant, but it's got this nasty problem called quadratic complexity. In simple terms, every time you double the amount of text you're feeding it, the work it has to do doesn't just double, it quadruples. That's a huge bottleneck. It's just not sustainable. We need to get to what's called linear scaling, where doubling the input only doubles the work. That's the dream. And that brings us to our first shiny new Lego brick, state space models, or SSMs for short. Now, instead of having every single word look at every other single word, which is what causes that massive slowdown, SSMs are smarter. They process information one piece at a time, keeping this kind of compressed summary, or state, that just gets updated as it goes. It's a really elegant way to solve that scaling problem and get us to that linear time processing we need. Now, the real breakthrough that made SSMs a huge deal is an architecture called Mamba. And what it did was so clever. It made a simple tweak. It lets the model's internal guts change based on the specific words it's seeing at that moment. This gives the model a kind of content awareness, letting it decide on the fly what's important to remember and what's just noise it can forget. It basically captures the magic of attention without that crippling computational cost. And this chart just says it all, doesn't it? That giant bar on the left, that's the cost for transformers. You can see it just skyrockets as you give it more to read. But then look at Mamba. It's that much, much shorter bar that scales so gracefully. And I mean, this isn't a small improvement. This is a total game changer. It opens a door to things like processing entire books or massive code bases all in one go. Our second new building block tackles a totally different problem, knowledge. So instead of trying to force a model to memorize the entire internet and its parameters, what if we just gave it, well, a library card? We can give it an external searchable memory. Think of it like a massive, perfectly organized encyclopedia it can check anytime it needs a specific fact. This is the whole idea behind something you might have heard of called Retrieval Augmented Generation, or RAG. Okay, so we've got these incredible new bricks, right? Things like SSMs and external memory, but that's only half the story. You can have the coolest Legos in the world, but if you don't have smart ways to snap them together, you're not going to build anything very interesting. So that brings us to our second big question. What are the new instruction manuals? One of the most powerful new ways to connect things is called Mixture of Experts, or MOE. And the idea is actually super intuitive. Instead of one giant network that has to be good at everything, you have a bunch of smaller, specialized expert networks. Then, when a piece of information comes in, a little router network, like a smart manager, sends it to whichever expert is best for that specific job. And research here is just moving at lightning speed. So, the standard way to do this is for each bit of data, each token, to choose which expert it wants to go to. But a really clever new twist called expert choice flips that whole idea on its head. Now, each expert gets to pick the tokens it's best at handling.
It's much more organized, kind of like a magnet pulling in the right tasks. This one simple change leads to way better efficiency and pushes the experts to get even more specialized at what they do.
So we have new building blocks and we have new ways to connect them. And that brings us to our third and final pillar. Because if you're building a totally new kind of machine, you can't use the old instruction manual, right? You need a completely new playbook for how you train it.
See, standard training methods, they have this subtle but really serious flaw. They're designed to find the absolute single lowest point of error. The problem is, sometimes that point is at the bottom of a very narrow, sharp valley. The model might perform perfectly there, but if the input data changes just a tiny bit, its performance can completely fall off a cliff. It's very brittle.
And this is where a much smarter training technique called sharpness-aware minimization, or SAM, comes into play. Instead of trying to find that one sharp, narrow valley, SAM actively looks for a wide, flat basin, like a dinner plate, where the error is pretty low everywhere in that neighborhood. Models trained this way are way more robust, and they generalize so much better when they see new data they've never encountered before.
All right, we've talked about the three big pillars: the new building blocks, the new ways to connect them, and the new playbooks for training them. So now let's put it all together and see the incredible new picture that's starting to emerge. This is basically what the future AI development process looks like. It's a whole stack. You start by discovering the best components. Then you figure out the best way to compose them into a larger architecture. After that, you pre-train them in this modular way. Then you fine-tune that composition for specific tasks. And finally, and this is the really cool part, you create systems that can keep growing by adding new pieces over time. This slide really just nails the paradigm shift. We're moving away from building these giant, monolithic, inflexible models. You can think of them like statues carved from one single block of marble. The future is compositional. It's about building adaptable systems from these interchangeable, specialized parts. It's much more like building a dynamic city that can grow and change and adapt over time. So, if you take away just one thing from this entire discussion, please let it be this. The race isn't just about making models bigger and bigger anymore. The next huge leap forward in AI is going to come from getting much, much smarter about how we compose them. So the next AI revolution, it isn't going to be a single new architecture that just replaces the transformer. No, it's going to be a whole new philosophy of building. It's an entire toolkit of new parts and new rules that will let us create systems more powerful and more adaptable than anything we've ever seen. So the only question left is, what are we going to build with it?